Welcome everybody to the San Jose Astronomical Association Astro Imaging Special Interest Group meeting for July of 2020. We are very happy to have Dr. Gaston Baudat, PhD, the creator of the On-Axis Guide, or the ONAG, and president, I believe, of Innovations Foresight, a company that makes a lot of different kinds of software and products for astrophotography. Dr. Baudat is going to talk tonight about collimation using artificial intelligence and his new product that is forthcoming. So I hand it over to you, Dr. Baudat.
Thank you very much. Let me be sure I can share my my screen and share it. So you should see my screen now, I guess.
It is coming up, yes.
Yeah. Okay, good. You see the presentation full scale?
Yes.
Okay, perfect. So I think the way I'm going to approach this is, first I have a slideshow to give us some introduction and concept on this collimation and optic and aberrations kind of things, and then I'll do a live demonstration on the bench I have here. Usually when I do the presentation, I'm facing people live, which means I can actually show the bench and do the manipulation. So this time it will be a bit different, but you will get the idea, I'm sure. So the title is Collimation using artificial intelligence, but basically it's collimation by the numbers. The idea is to collimate, align the telescope using some kind of quantitative information. And that's not new. You can do that with tools out there, like Sharp-Karpman sensor, Wavefront sensor, other kind of tools. The difference here, it's the approach and the fact you don't need any specific hardware to do the work, as long as you already have a camera and a focuser. So I'm going to give us some introduction on some concept, and then we'll go from there to a bit more application aspect. So, you know, collimation of a telescope is basically aligning the optical surfaces. We are assuming now, at least at that stage, then the optical surfaces are good figures. They are not the problem. Though we can do analysis of optical surfaces as well, which would be for people making mirrors or those kind of things, but that's a different discussion. So the main reason we do collimation is because if we don't align well enough those optical surfaces, we get aberrations. And the typical miscollimation or misalignment are things like, you can see my mouse?
Yes.
My cursor? Okay. So you can see you may have a tilt of both mirrors in the example of a reflector, or tilt of one of them, or offset, or a combination of these. And if they are large enough and you don't need much in optics, you get some level of aberration. And the type of aberration is a function of what kind of collimation problem you may have. So typically tilt, tip, offset kind of things, let's say the secondary and first mirror are not aligned well in a reflector, leads to astigmatism and coma kind of things. Those are usually off-axis aberrations. When you are on axis, they shouldn't be there, and if you see some, it's probably because you have a collimation problem. Spacing between mirrors or lenses will lead to symmetrical aberration, typically spherical aberration, which translate to fatter stars, larger full width arc maximum values. And of course, astigmatism and coma will lead to elongated star in the field. There is yet another possibility you may face is pinch optic. When the optic has been pitched too much stress, and you will see an example at the end of the presentation, you get very specific aberration like treefall, which are distorted star in some way. So below here, you see what you're supposed to see if you were lucky enough to take picture from space. Of course, we are seeing limited in normal life, but if you were diffraction limited, you will see this perfect pattern from space if your scope is perfectly aligned and you are on axis. Any optical system will have some level of aberration off axis because this is just the nature of the beast. And it costs more and more money to make a good off-axis image. That's why you pay more and more for more circle of imaging, bigger capability, because it takes more complexity on the optical design to give you near diffraction limit on the edge of axis. If you have astigmatism, which is typically of tilt tip or offset of the optics, you get this kind of patterns like a cross. This is a symmetrical astigmatism. If it's asymmetric, it may be an elongated kind of shape in one direction or the other. Coma, I think, is something it's easy to get because it's a very quite common aberration on the edge of the field. And if you see it, some of it on axis, you have a big issue with collimation. Coma is a comet shape like of PSF, the point spread function of the star, of the scope. And a symmetric aberration will be the spherical one. And those aberrations are maybe harder to spot because everything looks fine, everything is symmetrical, but in reality, you are pretty much like out of focus. And treefall is an example of aberration you may see when you have a pinch optic. Of course, there are other higher order aberrations possible, but those are the main aberrations you may expect to see in an optical system which is beside collimation made of good optical component. So we all face seeing limited condition on Earth. So collimation has an impact to our image to up to some level. It's you hear that very often, and we'll talk about Strel ratio and diffraction limited specification for a telescope. But the reality is, unless you have a couple of inch aperture or a very, very good sky, you are seeing limited. And even though your scope may not be diffraction limited, doesn't mean you have bad results. It's all about managing the expectation. If you go for a diffraction limited scope, that's great, but on the lab. On the actual life, on the sky, it does maybe not make much of any difference as long as the aberrations are under control. And we'll see a little bit what does it mean. So under seeing limited condition, what you can see on the left side is a perfect collimated scope. This would be a 10-inch SCT at f8, collimated. And you see what the REDs should look like. You have the central peak and the first ring. The other rings are too dim to be seen. But when you add a 2 arc second typical thing, you get this blob. You don't resolve the RE disk. But that's a result of a long exposure, like 30 seconds, 1 minute, 7 minutes, of course. If you use an eyepiece and you are skilled a bit, you may see the ring time back and forth through to the variation of the seeing. But usually when we image, we are facing long exposure kind of things where the seeing is average out and you get this kind of shape. Now, that means if you have some aberration, you may not spot them as long as they are not too much in amplitude or they are not too much asymmetric. They will not make much of any difference considering the seeing here and the aperture of the scope. Yeah, it's a bit more concerned. This is a miscollimated, same 10-inch SCT. And now the Strel ratio, I'm going back to this later, what does it mean, is only roughly 20%. And this one has coma and astigmatism. And you see the rings are spread and broken. And that would be the image you will get from sky, right? From space. when you look from diffraction, I'm sorry, from seeing limited condition, you see an elongated kind of star. The star diameter, the FWHM, is not very different than here, but the shape is not good. And I can tell you, I've seen many times over people complaining about elongated star, thinking this is a mount tracking problem when it was a collimation issue. And coma, which is one of the main aberration you will get when you have collimation problem, leads to elongated star pretty fast, even under seeing limited condition. So what do we do usually to collimate a scope then? The most common way is a qualitative approach. And it's all about the skill of the person who does the job. So we do a star test, and because we are not in space, we cannot get this kind of pattern. You can guess, I guess, from the eyepiece them, it's very hard to collimate that way. So usually what you do is you defocus a star, and you expect from the defocus pattern to assess the level of collimation. That's an example, again, from a 10-inch. I use a 10-inch because that's one of my scope. RCT, in that it's an RCT at f8. You see a defocus star, and this is the image of in focus, at best focus, the same star. That's seeing limited, so we can typically see the effect of seeing, which blur the rings and the resolution, also creates some kind of scintillation, those kind of variation of intensity and spike. This is a long time exposure, I would say 30 seconds to a couple of minutes, in order to average out the seeing. Now, it turns out in these cases, this is a well-collimated scope. And that's the good one. Now, how you know that? Well, usually because you have some experience. And my goal is to go from experience and qualitative approach from a quantitative way, trying to provide one way to do collimation by the numbers. So that's an example with the same scope. If the collimation is not good and you have some coma in this example, and you can see the effect of coma on a defocused star is this asymmetric pattern, which is an asymmetric aberration, leading to this coma shape of the star in focus. Usually that's not too bad to spot. So when you see that, you know you have a collimation problem. And most likely you're going to turn the knobs until you get everything a bit more center and symmetrical. A more difficult aberration to control is the aberration, spherical aberration. This is an example, again, under the same thing, of a scope with spherical aberration only, the same scope. You see, you have a nice symmetrical shape now. And between this and that, it's tough to say if the scope is well focused, well collimated, sorry. Now, here there is spherical aberration, and the result is a fatter, larger in focus, but symmetrical shape for the star, and everything will be blurred relative to that. Now, you can guess, if you do a star test by hand, you can guess about spherical aberration by doing defocus intra and extrafocal. And if both, by the same amount of defocus, both image doesn't look the same, then you have probably a spherical, even though they are symmetrical. And that's a technique used by Rodier, which is a technique using two images to do wavefront analysis and collimation. So what's happened if you have spherical and you think your scope is collimated because you see a nice symmetric pattern? Well, here it's an example on the same scope of the effect of spherical aberration on an actual image of M1, the Crab Nebula, and you see a perfectly collimated scope, you get this kind of image. And with the same scope out of collimation, but only spherical, you get that kind of blurry kind of situation. And you may not see that because you may think, well, your scope is collimated and what you have is a result of the seeing, which in this case is a result of collimation. Okay, so if we want to talk about collimation from a quantitative point of view. By the number, we need to talk a little bit about optics in terms of wave. Most of us have learned optics at school probably through the concept of rays, and then optical, rays kind of approach makes sense, but this is geometric optics. It doesn't provide any insight in terms of diffraction and all those kind of problems. So we need to go to the next step if we want to do a little bit more. So we need to go to wave optics. And the wave optics means taking in account the concept of wave in the nature of the light. So think about a star far away, which is always the case for us, and forget for the time being the seeing. We are in space. So the star creates a spherical wave, right? And this is an electromagnetic wave. And if you are far away, this wave looks like pretty much a plane wave when you see it, because you see a very, very narrow angle. The star is too far away. So you get this kind of oscillation of the electromagnetic field. And here is an image of the plane wave. The red lines being the peak, and the white will be the trough of the wave. And the wave is moving at the speed of light, of course, toward your optical system. This will be a perfect scope, which in this example is a perfect lens. And the goal of any imaging system is to map a point, which is here a star very far away at infinite, to a point on the image plane, on the focal plane, which means the plane wave in that case is translated to a spherical wave with the center at the focal plane, where the spot of the image of your object will be. So if you do that and you don't add the concept of diffraction, then you get a point, a perfect point, and that will be consistent with geometric optics, ray tracing. One thing to keep in mind is when you use a wave, there is a concept of phase, and we'll see that a bit later, which is important to analyze optical system. And you need wave optic approach or Fourier optics to deal with the concept of wave and phase information, which we don't have with ray tracing. Okay, the reality is you have another effect, which is a fundamental limitation of our systems for any imaging system, is a diffraction effect. And that's all about the wave nature of the light. And you couldn't explain this if you use only ray tracing. What's happened, you see that on actually any wave kind of things, like a wave on the water, when waves, and those are not plain wave here, but you get wave from offshore, and you have some kind of aperture obstacle here, then you get those kind of diffraction effect where the waves start to spread from the aperture in a kind of spherical pattern. And this is exactly what's happened with the light, except of course the scale of everything is much smaller because the wavelength is much smaller. But you get a plane wave coming from a target here, and it's a plane wave again because we are doing astronomy here, our objects are far away. And when you hit the aperture of the telescope, even if the optic is perfect, by just the aperture will create this diffraction effect, the wave spread. That's why at the focal plane, you don't get a point. You never get a point. You get what we know as a point spread function, or the airy disk. And if everything is perfect and the optic is perfect, then you get those kind of rings around the central peak. And this function is known as a Bessel function for a circular aperture. It's the best you can ever get because the nature of the light, which is a wave, you get the resolution. To make this is tighter and tighter, closer to a point, you need to increase the aperture size. The bigger the aperture, the tighter the size of the peak of the PSF, and closer to a mathematical point you become, closer to a geometry optic situation. So just a word about the straight ratio, because you hear that many times over, I'm pretty sure. And it's a very good way for close to collimation scope to give you an idea of the performance of an optical system, because you can summarize the performance through a single number. But it doesn't tell you what kind of aberration you actually face, if any. So you have to consider the Strel ratio as a good way to give you an idea where you stand only when your system is close to the diffraction limit. Otherwise, many different types of aberration may give you the same Strel ratio. So what is the Strel ratio for a given scope, for a given optical system? It's the ratio between the peak of light intensity you will get if the system was perfect, diffraction limited for a given source, like a star, and the actual value of the peak you get on your actual system. And this value is always below the peak of the theoretical peak, because the light spreads across here a little bit more, because you have always some level of aberration in any optical system. Now, that's not taking in account seeing, right? I'm still in space. So, and I can get the Strel ratio from measurement in the lab, for instance. And this value here tells you basically the lower it is, the more light is spread across the peak versus the perfect optical system. So you get an idea of how good your optic system is. So basically, the Strel ratio is one way, a simple way to tell you if you are close enough to the best optic you may ever get. And by definition, we assume that when the Strel ratio is 80%, we are diffraction limited from a practical standpoint. The reality under seeing limited condition, if the aberrations are not too asymmetric, probably around 40 to 50% is good enough for most scope, as long as you have large enough aperture, like 6, 8, 10 inch, because your seeing is probably between 1 and 2 arcseconds, and higher Strel ratio is not going to make much of a difference. But again, because for the same Strel ratio, you may have different kind of aberration. If those are too much comma-like, you may still see an elongated star. Okay, so why we are talking about wavefront? Because this is a very common kind of things you may hear when you do optic. And wavefront phase error. The idea of wavefront is to look at the light from a wave point of view. And there is a relationship between the way the wave behaves and the optical aberrations. So if you think about a sample case when you are out of focus, just to give you a feeling, my goal is not to go to the detail of it, but just give you a feeling what wavefront means and what how we use this information to infer the optical performance of a system. So think back to my plane wave coming from a star far, far away. The perfect lens is supposed to focus this yellow wave to the focal plane, to a point with a diffraction pattern, because the aperture is limited. But in reality, let's say I made the decision to place a sensor plane too close to the lens. So I'm intrafocal with some defocus, mechanical defocus, right? There is no problem with the optic here, just the way I place my plane, my sensor plane. Well, my expected wavefront is a red one. I expect, if I was in focus at that location, to have this kind of wavefront. But in reality, I have the yellow wavefront, which is lagging behind the red wavefront, my expected wavefront. So, and you see the lag is bigger and bigger the further away you go from the optical axis. And that means the wavefront error, which is a phase lag, is larger and larger when you go from the center to the edge. And you can see, that's why you have those rings when you defocus. And there is no central obstruction here. So you don't have a donut shape, but this will be a refractor in that case. You see those rings are related to the fact that when the lag hits one wavelength, you have a 360 degrees phase shift, and you get a peak or a trough in the diffraction pattern. And here you see all those rings who tells you by how much you are actually defocused, how many waves of defocus you have. And you can count them and know what the defocus value would be. You can actually use that to know how much out of focus you could be, if you can actually retrieve those. Here, of course, I'm in space, so it's easy. In reality, you are not. But the goal of this is to tell you, by looking at the phase error between the expected perfect phase wavefront and the actual wavefront, you get information about the kind of aberration. And if you can retrieve the phase information, you know pretty much everything about your optical system. So this is an example of a perfect optical system, and on the top here, and I use ray tracing now, because the rays are always orthogonal to the wave, right? To the wave of the light. So in a perfect system, all those parallel rays for a plane wave will converge to a point which will become this airy disk. And I told you before, then the shape of the wavefront after the optic of the telescope is a spherical wave converging to one point. And that will be the shape, basically the section of the spherical wave in this example. So you get your PSF. So you translate a plane wave to a spherical wave, and you get a point, almost a point, because diffraction. If you have aberration of the optic for any reason, collimation is one of them, you see the rays may not converge to a point here. And adding the diffraction, you get those kind of effect, which would be the comma here. And you see the wavefront here is not a spherical shape anymore. So you have a piece of the wavefront is leading and piece of the wavefront is lagging the spherical wavefront of a perfect optical system. And those lag and lead are typically shown in wavefront diagram, color plots, in color. So this is the error between a perfect spherical wave expected and the actual wave you see from your system. So if your system is diffraction limited, then there is no difference, zero, between the spherical and the actual wave. And you get, as a result of the wavefront, you get the PSF, which is an airy disk. That will be an example where piece of the wavefront is leading and piece is lagging. Blue is lagging, red is leading. Peak and trough on the wavefront versus the spherical one, and you get comma. Now, if you have those two corners leading and those two corners lagging, and then you get astigmatism. And you have a symmetric pattern like this one where you lead front and you lag on the edge, then you get spherical, symmetric aberration. So there is a connection between the wavefront error and the shape of the PSF, therefore the shape of your star and the quality of your system. So technically what we do when we do optics, we use a tool named Zernike polynomials, which is a mathematical way to express the shape of the wavefront error. It's like the Fourier transform in some way. And what's happened is you see this kind of deformation here, like we had here on the wavefront, with some peak and trough here, combination of aberration. Well, you can express it as a combination of some spherical, comma, astigmatism, and defocus in this example. So you can do a decomposition through a basis of many different shapes, more and more complex, like you do with a Fourier decomposition with many more frequencies. And the calculation tells you how much of it you need with a sign in order to rebuild what you saw. And that gives you how much aberration by kind of aberration your system may have. So having access to the wavefront allows you, through those kind of Zernike polynomials techniques, to actually get a quantitative idea of the type of aberration and how much of it you may have on your system. And those tell you about your system performance, but also about what kind of collimation problem you have. So that's an example of a miscollimated scope, a very simple one. That will be a sample lens. And if you take this one and you are on axis, you get, in this example, perfect wavefront almost, and your stride ratio is 91%, you have a nice PSF, as you would expect, at the focal plane. My optic is aligned. Now, if I offset my lens versus the optical axis, where I may start to see, which is common, especially if you have only one lens, which we never have. In fact, we have more than one for that reason, to make a better scope. Then I start to see this typical pattern of chromatic aberration with a leading and trailing edge of the wavefront, which leads to this comma shape of PSF, and the thread ratio dropped to 37% just because I offset my lens or my mirror or whatever here. It's a kind of collimation problem. And of course, the result of that is a drop in thread ratio, but also in modulation, transfer function, and quality of the image. So now I'm not going to talk about the math here, that's not the goal, but from the wavefront, if you know the wavefront, you can compute the PSF. That's an easy one to do, mathematically speaking. You just have to compute the Fourier transform of the wavefront and take the square of it, square of its magnitude, and you get the PSF, basically the image you see on your sensor. So having the wavefront, you can compute the PSF. The problem is the other way around. And that's where it becomes more complex, because there is no easy relationship. There is, but it's not that easy, between the PSF and the wavefront. And that's what you do when you do collimation with an eyepiece. You try to guess from the PSF the aberration of your scope, basically the collimation of it. And the goal here is to provide you that in terms of wavefront and therefore numbers. So to make a long story short, there is a way, by analyzing the intensity and the shape of the defocus star, which is looking at the irradiance of the defocus image of a point source, to retrieve from there the wavefront using some kind of mathematics. Normally, if you use the Rodier techniques, those kind of things, they try to solve this differential equation in an iterative way. And it's not an easy one to do, but you can try to do that, and this equation is valid only if the defocus is not too large and the aberrations are not too bad. Otherwise, you don't have a very nice way to solve the problem. And you have, by the way, you have to find the best wavefront to match what you saw, which means you may have problem of convergence because it's a nonlinear optimization problem. And you have to do it every time you get a new image. So our approach is quite different. We don't want to solve the problem using a direct model like this one. We want to solve the inverse problem by just learning using a learning machine, here a neural network, the relationship between the wavefront and the aberrations directly. And we know there is a relation between them. Yeah, this is known. This relation is partially this equation, but it's not enough to describe perfectly the relation. But the relation does exist. That's all we need to know. So if you defocus a star, then the information from the defocus carries all the information about the aberration. Therefore, you can learn, and we use a neural network for that, to map the image of a defocus star to the aberration. In that case, what we want to do is just to learn those Zernike coefficients who tell us how much aberration we have from any kind. And by the way, we can in the same time learn what's known as a Fried parameter, which is a measurement of the seeing when you are under seeing limited condition. So with neural network kind of techniques, you can make a lot of samples, and I do that only by calculation. I actually don't need to get data from an actual scope. You can do all the mathematics from pure simulation. You make 100,000 millions of samples with random errors in a given range of aberration and seeing. And you tell the neural net to map the image here of some kind of aberration to the actually output value you use to make those image. And eventually the system will learn the relationship. And the good news is you spend maybe, in that example, I spent a couple of days to run it takes a couple of days to actually build the database of samples. And then he may take a day to train the neural net to learn them. But you do that once only. When it's done, you do a mathematical model for a given kind of scope. Then you don't have to be worried about any kind of calculation and optimization during the time you actually use it, because now it's a direct kind of forward model. You come with an image, you just plug the image at the input of the neural net, you do the calculation, and you get the output straight. There is no iteration, no guess, nothing like that. So this is an example of a bench. So I told you before, I usually show you the bench live during the presentation, because that's where people get a better idea of the reality. So the bench is a very, very small refractor. I made it such I can carry it with me in a carry-on luggage in a plane when I go from a conference to another one. But it's very close to what you actually do. It's an optical bench with a single achromat. It's roughly an inch, right, with a focal length of 300 millimeter at 12.5. And I have actually I have artificial stars, more than one. And I'll tell you why, because the nice things with this technique, you can do off and off axis analysis in the same time. So I use actually 7 pinholes of 10 microns to simulate stars, and I defocus them. So if you look at the bench, you couldn't see it now, but he's on my desk now. You have here the scope, which is made of a single achromat. Here there is a beam splitter. It's a pellicile beam splitter, such it doesn't impact the quality of the optic. On the vertical leg, you have a pinhole with a light source, which is my artificial star. Actually, pinholes, there is more than one. There is a XY table to be able to align everything. And on the other side of the beam splitter, you have a camera. It's a 1600 monochrome to take a picture. So what's happened is a light from the pinhole, which is my star, at the focal plane of my achromat, is imaged here as a parallel beam, plane wave, but there is a flat mirror in front of it, a very good flat mirror, very flat, which reflects the light back through the beam split, through the lens, the achromat, and through the beam splitter to the camera. So this is a way to do a double pass analysis of the scope, like if you had a star. Of course, I don't have anything here. I'm on the lab. I have an artificial star, like if it was in the sky, except like if I was in space. So we do a double pass kind of thing. So we have a flat mirror here. So what I'm going to show you is live, taking picture from this camera every 2 seconds, how the defocus image is analyzed to retrieve aberrations across the field, which you can use to know the quality of your optic and the kind of aberration, and therefore the kind of collimation problem you have. You have no data with values to tell you how much astigmatism come out. And if you know the optical layout of your telescope, and you can actually connect those values to the miscollimation error, exactly by how much the mirror is offset, and all those kind of things can be retrieved if you have the optical layout from the aberration and the value of the aberration, including the sign and the type. So before I show you that, I need to tell you about what you're going to see on screen. I use 7 pinholes to simulate 7 stars in the field, because usually when we do collimation, we do an axis. We bring the star at the middle, but the reality is any optical system has some aberration on the edge. Having the capability to get aberration across the field, if, for instance, if you use a star field, is useful because you get an idea about the performance across the field, including the field curvature of your system. And if it's not very well collimated, field curvature will not be symmetrical around the optical axis, which is a typical sign of collimation problem. So I have 10 microns here, and for each of them in real time, I'm going to retrieve, using the neural network technique, the wavefront and their aberration at different locations in the focal plane of the scope. So to show you that, I need to stop for a little while the presentation here and start the software, which is Python driven. So it's interpreter is not that fast, but it should be fast enough for the goal. And you will see the image of the pinholes and the analysis live of the aberration for each of the pinhole. So stay with me, it's of course slow. It is always slow when you do a presentation. It's coming. And the back, well, here we are. So what you will see here, you see now I have my 7 pinholes. So now they are not perfectly aligned with the red cross, which is the center of the chip and the optical system. So I'm going to move the stage. That's because temperature change and stuff are moving. So I'm going to turn the knobs here, try to put everything close to the center as much as possible. Not that far now. So give me just a few minutes, probably less, to do that. Close enough at least. So what you see are defocus image. That's a refractor, so there is no central obstruction, right? But the calculation can be done and is done with central obstruction. That's not, you have annular Cernicke coefficient who actually use central obstruction. So what you can see here, I'm on axis here, and I have 3 spots, 3 defocus star of axis on both sides. So the first things we can do, and think about that being your defocus star, you know. Of course, they will not be on a line, most likely they will be across. But so the first things we can do is a wavefront analysis. And if I do that, you see here on axis, the pinhole 0 is the on axis pinhole, and you get a bunch of data. And of course, the software at the end you're going to use is not going to give you this kind of things that way, because this is more for me from a optical point of view, a mathematical point of view to look at it. But what you see here, it's how much defocus we have, which is what we are 65 microns to the perfect defocus expected value, so close enough. We have a strain ratio of 99.6%, so it's pretty much diffraction limited. This is the wavefront error, leading, trailing part of the wavefront. You see the wavefront error here in waves, in wavelengths. You know, so it's 40 milliwave to minus 40 milliwave, minus 30 milliwave to plus 30 milliwave. So it's very little. And you see on this bar plot the different level of aberrations. A little bit astigmatism, comma, trefold, very little, and spherical. But everything is very, very small. So I'm pretty much diffraction limited. So now if I move away, go back here to the actual pinholes, I was here. I think I have a way to show that. I was analyzing this one. I can analyze any of them and move here. This will be 0, plus 1, plus 2, plus 3, or minus 1, minus 2, minus 3. Let's move here and see what's happened. So you see the astigmatism is roughly, forget the sign, 36 milliwaves. If I move away from the central one, I have more astigmatism. And that's typical. You get more astigmatism off axis because it's a simple achromat. That's why you need more than an achromat probably to do a good refractor to correct for those astigmatism off axis and comma. Now my astigmatism is 67, then it goes up to 112, and at the third last pinhole at the edge of the field, I'm at 185. And that's just normal. So again, it's a nice achromat, but it's not the way you want to do a good telescope. You will need more than one. So now, what I'm going to do here, I'm going to show you something you need to be careful with when you do optical kind of mechanical alignment and tightening screws. I'm going to tighten a little bit one of the screw there are 3 screws who actually keep the mirror on his mount. So I'm going to tighten one of the screw which is at 45 degrees, just a little bit by hand. Is a thumb screw. You will see what's happened when I do that. On axis, you see a jump in astigmatism, and you can see that on the actual image. You see the shape of the defocused star is elongated now, like almost like an egg, and that's coming from the fact I warped the mirror and I didn't tighten much the screw, to be honest with you. That's very sensitive. We are talking about optics and nanometers kind of thing. So you see the effect on the wavefront, and now you have dropped on the strail, not too bad, 92% though. A big jump on astigmatism. Spherical remains the same because it's all about the lens, not about the mirror. So if I tighten a bit more, and this is live, you know, the system is taking images, analyze them, and give you back. So it's even worse. Now I have almost 120, 600 milliwave, 0.6 wave of error. My strail is now pretty bad, 454. Before I look at the PSF, the one I will see from space, that's what I get, with a typical sign of astigmatism. This cross kind of things. Now, if I release now the mirror fully and wait until we get a new image from the camera, I get back to my diffraction limited kind of pattern. This the PSF of my telescope. And the wavefront is back to something quite nice with a high strail ratio. So these kind of techniques can analyze the optical performance of the scope across the field at once, using only a camera you already have, and a focuser to defocus a known amount. And using those aberrations, you can retrieve information about the kind of collimation error you may have. So of course, here I'm in a lab, and the image is pretty nice. Oh, by the way, I should show you that you can also compute the field curvature, because I have 7 pinholes, so I can look at the field curvature. And you see the field curvature in red is the theoretical one from this achromat. Because I have the mathematical model of the achromat, I can compute it. Of course, the achromat is not perfect, probably. This is what I get from analyzing my 7 pinholes using the wavefront and the neural network, retrieving the Zernike coefficients. So the next things I like to show you is over here, is how it's going to look like for users like us when you want to use that on actual star. So we're going to add the capability of wavefront analysis to provide you quantitative information for collimation on our SkyGuide and SkyGuard software. So for the people who know it, it's a software for auto-guiding and autofocus if you have an on-ag live while you are imaging with the shutter open. And there will be a third tab here, where you can analyze the image of a star in a field or more than one. Today is a beta version, so we have actually to load the image from a file. But eventually the image will come automatically from the software, because SkyGuide can guide on any kind of target. It doesn't use a guide star. He's using the whole image. So a defocused star will just be fine for guiding or any extended object or more than one star. And the system will automatically track that and recompute the wavefront as you go when you are turning the knobs for the collimation. So, okay, so here I have an example. This is the actual defocus image from a telescope. It's a 0.6 meter, roughly, I think, what is that? 2 feet aperture. It's an RCT from an observatory in France, in Ardèche. And Cyril Cavador, who actually wrote the software Prism for the people who know it, went there and was kind enough to test our software for collimating this scope. He used to do collimation with the Shackhartman sensor, which is a piece of hardware, but that costs some money and needs to be placed instead of the camera. But he used our software instead just by defocusing the image. And that the scope needed some collimation, and you can see here the wavefront and some data here. So don't look at the seeing value. 3.3 arc-second is wrong because the mathematical model from the neural network used was not the model for a 0.6 meter scope. It was for a 10-inch, which means because that the seeing calculation was wrong. In fact, it was around 1.5 arc-second. But what you see here, it's the thread ratio is 14%, not very great. The RMS wavefront error is a quarter of a wave, and the peak valley is 1 wave. And you can see the peak here and the valley of the wavefront with a strong kind of astigmatism, but mainly comma. And you see the comma is the main parameter here. So if you look at the PSF of that scope from space, rebuilt from the mathematical Zernike coefficients from the analysis, you get that. And we see typically the comma. And that's exactly what you see when you actually use the scope for imaging. Now, this and RC are not easy to collimate. So what he did is spent roughly an hour to use our software for the first time ever, and did a collimation by a tilt tip of the secondary. This scope requires a special tool to actually move the secondary offset. So he couldn't do that. So he said, I'll do my best with tilt tip only. So it took an hour, and what he got after an hour was, take to load the final image here, was this kind of PSF with some comma left, I'm sorry, astigmatism left, but much better. And we're seeing limited, think about this is a quarter of an arc-second diffraction limited pattern because the size of the scope. Under a 1 arc-second to 1.5 they have there, it's still very small comparing to the seeing. So they came to the conclusion this is good enough. They don't need to worry much about the offset of the secondary mirror to make it even better. If you look at the result now, the straddle is 43%, but mainly the aberration is symmetrical. The RMS dropped by a factor 2, which means there is way less distortion on the wavefront, is much more symmetrical. PTV is the same, but it doesn't matter here. Forget about the seeing again. And with the wavefront, yes, I show you the wavefront. You see now is left over with some astigmatism, which is typical of an RC with an off-axis secondary mirror. We could do better, but wasn't the idea. They couldn't do it back then anyway. So, but that's the way the software will work, except you wouldn't have to load the image. You will automatically take the image as they come from your imaging camera while guiding full frame and doing the analysis of one or many of them if you have more than one star in the field. The software beta should be available sometime in August. And eventually we'll have a full release of the software a little bit later in the fall. That's pretty much it, I think, for me at that stage. So if anybody has some question, I'll be happy to answer them.
Okay, I'm watching the chat. Anybody have any questions?
Let me release my presentation, right? So you can see me.
Absolutely fascinating stuff. So I am wondering, somebody with an RC, like your 10-inch RC, that may be off as far as mirror spacing and also off as far as tilt of the secondary and tilt of the primary. How do you work through all those different things?
Well, that's a very fair question. There are very fundamental rules first. If spacing is part of the problem, the result is spherical and symmetric aberration. and the magnitude, more the sign of it, tell you if you are too close or too far with the mirrors. So you can move them in the right direction and see what's happened. Now, if you have an asymmetric aberration like coma or astigmatism, it's probably because you have a tilt or an offset between the mirrors. And the way to do it now would be to change a bit and see what's happened, if he makes better or worse. At that stage, the software will provide a feedback by number and tell you going on the right direction or the wrong direction, and give you an idea of the Strel ratio and the direction of the aberration. And you probably saw on my just demonstration of the software, there is actually a target with a dot moving, and there will be an history of dots which tell you in which direction the aberrations are and by how much they move away from the center, which is a 100% Strel ratio. Now, in the longer term, our goal would be to build a database of telescope for which we know the layout, optical and mechanical, working with people making scopes, such we can tell you which knob needs to be turned by how much. At that stage, the software will tell you what do you get. And when you actually turn the knob, you will see if you make it better or worse and in which direction you do that. That's exactly what Cyril did. He didn't know much about it, so he turned the knobs and found, okay, when I do this way, it's better. When I do that way, it's worse. And in that direction, and getting the feedback was enough in an hour or so to get the level of performance he was looking for. So every scope will have a different kind of approach, because RCT are much more sensitive because those are hyperbolic mirrors. They have their own optical axis and they need to be aligned tilt and offset wise. The SCT scope are much easier because they are spherical secondary mirror. So it's just tilt is enough to solve the problem. So we can provide that in longer term is some kind of help in order to know which kind of knobs need to be turned, if we can work a bit more with the people making scope. But just the fact you already get numbers and you can repeat and see what's going on and get a trend is very useful, because you know if you're going better or worse. And with some experience, it's pretty easy after a while to have a good idea for a given scope what's going on. The other things I haven't talked about, which is not yet implemented, is we're going to show you what the image of an actual star under seeing limited condition will look like with your collimation at best focus, which means today what you see are the aberrations and the PSF, right? Like from space, which you never get. So we're going to show you, okay, that's the shape of the star, the way it will look like if you stop your collimation there versus the perfect one you could get for your seeing conditions. So you may decide it's good enough. I don't want to go much further. You saw that with the 0.6 meter scope, because it's a large aperture. You don't need 100% or even 80% of Strel ratio under seeing limited condition to do a good job. 50% was good enough. So we're going to add those kind of features to tell you you're good enough. You don't need to go further. I mean, people want to be diffraction limited because they pay for it. The reality is, well, they need probably to invest the time they want on imaging and not more than need on collimation.
Sure. Anybody have any other questions? Okay. Well, I really look forward to maybe beta testing with you and
yeah, sure,
checking it out. So
yeah, one question here. You talk about space and with actual condition on seeing. This technique can be used also with an artificial star, like I don't know, 50 meters away or something like that, in order to improve the quality of the analysis?
Yes, that's a very good question. And this is related to another one, I guess, which is you can use this technique for people making mirrors as well. You know, when you are doing the polishing and look at the figure of the mirror. Yeah, you can actually do a mathematical model with artificial star at some distance from the scope, as long as you can focus. Of course, somewhere. I mean, if you are too close, you may never get the level of focus or defocus you need. But yes, if you can do that, we can do the mathematical model for a star which is close by, an artificial star. What you saw here was a double pass with an artificial star and a beam splitter. But if you have an actual pinhole, you can buy those in many places, right? And you place this artificial star, let's say 50 yards away, 100 yards away, whatever. You could use that, and we can provide this capability. That's part of the ID too, as well as providing capabilities for people who are doing the same to test mirrors, optical systems.
I have a question. Is it possible to use here some sort of ray tracing techniques to simulate different optics systems?
I'm not totally sure I understood the question. Can you?
Yeah. So, is it possible to apply some sort of ray tracing methods to simulate different optics designs for telescopes?
No, when we actually create the samples for the training of the neural network, we use wave optics, Fourier optics, because if you use ray tracing, you don't get the diffraction effect. Because by nature, ray tracing is geometric kind of imaging, and it's okay to find out where the image will be, but you don't get the diffraction effect. So all our calculations are based to Fourier optics and diffraction theory, and it gives you the same solution than ray tracing finally, except it takes in account the wave nature of the light and the diffraction effect of the scope.
Okay.
One other question, just to clarify. Let's suppose that tomorrow I will receive the software. You mentioned that that software need to have, let's say, the model and the artificial intelligence parameter all trained inside in your database. I can do that with my scope, or I have to, let's say, be sure that my scope will be in your database. I mean, in another way, you will furnish a database, or we have to prepare that, and in which way?
Well, it's a very good question. So the way we're going to sell the product is the wavefront analysis feature you saw on the software will be standard with SkyGuide and SkyGuard. However, what you will have when you buy it, you will have example of images from a database and some capability to do simulation, create aberration, and look at the result and the effect of the analysis. Now, when like a software, I think most of us probably know, which is Aberrator. You can create aberration and see how does it look. It will be the same kind of things. If you want to analyze your scope, you will have to buy the model for your scope. That's the way we're going to sell the technology. So if you have a given scope, then you pay for a model of the scope. The model is a matter of aperture and central obstruction. I guess I told you before the seeing value you saw on the simulation was on the actual data was wrong, because I use a 10-inch model for a 0.6 meter scope. And the seeing is very different on the 0.6 meter versus 2 feet versus a 10-inch. So that's why. So we will have models by kind of scopes. And that's why we're going to have a library, and you can say, okay, I have let's say, pick an example, right? You have a C11, some kind. So you pick the C11 and you can buy the model for the C11. That's the way we're going to sell it. The tool behind it to do all the interface and calculation and show you the result and all that will be standard from the software. So if you buy the software for guiding and maybe focusing if you have a non-ag, then you will have the wavefront capability already there. You just have to buy a model if you wish. Then you can learn to use the tool before you actually buy your model.
Okay, thank you.
Thank you very much. Anybody have any other questions? Okay. Rob?
Hang on, I was going to ask. So I have a couple of RC telescopes, and as everybody knows, they're pretty hard to collimate. And so I was just wondering, in this method, is it going to be the same where you have to do sort of all the analysis on an on-axis star, and then shift to the one or more corners to sort of redo the analysis in the corner stars? And then, I mean, a big part of the problem is you have to iterate over those two.
Yeah.
And sometimes you get lost, and so I'm just curious whether or not you're able to sort of derive the whole thing from the on-axis star with this technique, or you're still going around all the corners and doing the same kind of iteration.
Well, that's a very good question. But first, if your scope is well collimated, you shouldn't have any asymmetric aberration on axis, like comma. If you have any, that means you have out collimation problem anyway. So the most common way to do collimation is to start on axis. And when you are good on axis, you may do a check off axis to see if it's still good enough, right? Of course, you may do two corners to be sure it's symmetrical kind of things. So I think one of the things I tried to show during the presentation on the bench is you can do, if you take more than one star in a field, like a star field, you can analyze all of them at once and get all the aberration from the center to the edge. Like you saw for my example where we see the field curvature, the actual one versus the theoretical for the achromat. This is the kind of things we can show. So you will be able to actually use more than one star for the collimation. And because this is part of our full frame guiding technology, when you turn the knob, the system will automatically recenter all the star field where it was, because it's processing the whole image. This way you can stay, you can get, if you wish, all the aberration and all the analysis at once with a single image of multi-star. You don't have to move as long as you have more than one star in the field.
Okay, that's helpful. I guess another question is, how much CPU power do you actually need on the computer that's doing the analysis? I know building a model like this takes, graphics card or something like that, but a lot of us have kind of underpowered computers on the telescope, and I just wonder what you're targeting for performance of, to actually run the neural net.
Well, the good news here, it's the hard work is done beforehand. The creation of the database and the learning of the neural net is done on the cloud. It takes days. It's done once. When it's done, the only calculation you do on your computer is feeding an image and computing the output feed forward. So the time it takes to compute the output of the neural net is very little. I mean, those are not. So I'm running that on the standard laptop. I mean,
okay, well,
it takes probably more time to download the image than to do the calculation.
Sure, okay. I mean, everybody who's run StarNet knows that it can, it's a different problem, obviously, but it can take minutes to process that.
No, but all the calculation of the neural network, all the learning process, all of that is done before. It has been done.
I understand that's usually orders of magnitude more processing power required for that. But even running the network in the forward direction can sometimes take quite a bit of CPU. So
no, this one is not. No, I think I haven't checked the detail, but my guess on my laptop, which is very simple, I mean, this common laptop, I bought it 4 years ago, I think. So it's probably pretty much behind now. But it takes probably 100 milliseconds to do the calculation.
Okay.
Kind of things. Yeah.
Okay.
Probably longer to actually display the result and get the image for the graphic or stuff like that than the calculation itself.
Okay, thanks.
Another question, talking about performance. In your experience, I have an RC, and of course, I've been crazy about collimation and this and the other. So at the end of the story, I resolved to use an OTEC hardware in order to collimate mine. In your experience, I don't know if you have or you have used these kind of things, but comparing an hardware way and the software way. There is advantage, disadvantage. I'm not talking about. I'm talking about precision, not of course the hardware is more problematic because you have to mount, align the hardware, this and the other. In this way, in your way, you have not to do all these kind of things. But in terms of precision,
well, first, I think when you use probably laser kind of things, right, for aligning, you get a first good guess of the alignment of your system and aligning the mechanic and everything close as you can. However, we are talking about optics here, right? So even if it looks great on a laser kind of pattern, you may still on the optical performance. So laser alignment techniques are useful to get close, but it's not enough most of the time. So you need a way to know, optically speaking, how close are you from the performance of the system. And that's where you need some kind of optical way to quantify, either because you look through the eyepiece, right? Or you get numbers like we provide here. So the laser is alignment techniques are useful just to bring you close. That's typically on RC, it's not good enough because you have those hyperbolic mirror where you don't, in optics, you know, everything is made of rubber, right? You just move a little bit anything and it's a big change. We're talking about nanometers, right? So, you know, it's nothing.
yeah.
And so for aligning, my experience, because I have an RC2, my experience has been, I used those techniques before and used those Takahashi telescope to align everything. And they do a good job to give you an idea where you are. But I couldn't ever get the performance of my scope until I was able to do wavefront analysis, having a way to quantify the optical performance at last. Until that software, I use a Shack-Hartmann sensor, which is a wavefront analyzer. So you take away your camera and you place that sensor. And it's a wavefront sensor made of micro lens, and it's doing pretty much the same thing that I'm doing. Provide you the wavefront and everything, and you can. And it works great to align my RC. Now, of course, the difference between this and what we have, you don't even need the hardware. I mean, the wavefront analyzer anymore. My guess is if you use I think the most useful tool I had for my scope was the Takahashi telescope, because there is a black dot in purpose on the secondary. If you align it good enough, that's a very good beginning to your collimation journey.
Yeah.
I can say that I learned that I've been using too much force with my push and pull screws on my RC when I've been adjusting it, just by watching what you did. So,
yeah, well, I have an
hand.
example. Cyril Cavador, the guy who wrote Prism, we spent some time to test our technique with his help, and he has a very nice example of an RC where actually the mirror is a little bit too tight, and you can see the trefoil I was talking about, the pinch of the mirror on the wavefront. You see the peak and trough at 3 locations. And, you know, you don't need much. I mean, I was very surprised myself when I built everything on the bench, how much a little too much torque on any kind of screw give you, you know, a pinch optic kind of effect. You don't need much of anything. And that's probably why you pay way more for some high-hand scope having very, you know, the same optics. I mean, if you look at the RC, I have an Astrotech, right? So it's because it was a budget kind of choice. They have a very good GSO optic, and the GSO optic, I think, is very fine. The optic is perfect almost. Where are the differences on the mechanic? The way the mirror is mounted and the way you can adjust it, and how much it keeps its collimation over time. That's where you pay the difference in price between maybe those kind of GSO telescope and plane wave or whatever. You know, at the end of the day, you pay for that. To go back, by the way, if people are interested, I'm going to put that on our website. We have a paper coming at the San Diego conference, SPICE conference, which now is online. of course. Nobody's traveling anymore. But the paper is a comparison between this technique and interferometry wavefront analysis using a phase cam, which is a golden reference, and a Shack-Hartmann. And that gives you an idea how accurate the techniques may be. We can actually be in a range of hundreds of a wave accuracy, which is way above what you need for collimation. In collimation, tenths of a wave is probably good enough for most of us under seeing limited condition. But the technique is very, very sensitive to little. And one of the goals was to see if we can use this technique in metrology, in other applications, beside astronomy. So for the astronomy, we don't need to go that far. Thanks from the atmosphere.
Do Hyperstar setups, the Hyperstar 4 is a new version of Hyperstar. Do you know if that would prove to be problematic in making a model in any way?
No, I don't think so, no. I don't see any optical layout which would be a problem for, I mean, at the end of the day, we use Fourier optics and a diffraction theory to build the samples. So as long as we know the layout, actually, I'm working as we speak with, try to remember the name, one of the laboratory here in US, forget the name. They run, I think, the largest world synchrotron accelerator, and they create X-ray beams. And that the goal is the X-ray beam.
I think it's SLAC.
I'm sorry?
Is it SLAC?
Yeah, it's I forgot the name. Just give me 1 second. It's should be able to
probably SLAC
to remember which one, because I have too many things in the same time, so I have a tendency to forget. But I have a meeting with them. We already have. It's the Brookhaven National Laboratory.
Oh, yeah, Chicago. Yeah. New York. Yeah.
It's New York, yes. And what they do is they use a synchrotron to create a X-ray beam, and they use the beam to test material, any kind of things, right? Whatever. They need the high energy beams, but they have a big problem. They need to be sure the beam is very well focused, collimated, put it this way. And you don't do collimation with lenses with X-rays. You can't. You do that with mirrors. Only reflection and total reflection. You cannot even use a coating. So it's very special. But their problem is to align their mirrors. They have few mirrors to keep the beam collimated on the target with an accuracy which is a fraction of a nanometer. Because we are talking about the wavelengths in X-ray are like 3 nanometers, not 500, like we have. But we have done some tests so far, and we go working with them. We're going to simulate those kind of problems with X-ray, which is very different from a telescope. But there is no reason this whole calculation wouldn't work for that. We just need to do the right calculations, and when we get the database, then we just train the neural net. I have done neural network stuff since 35 years, way before Google came to talk about it. So that's my part of my background is apply mathematics and machine learning. So I don't think Hyperstar will be a problem.
Okay. Thank you. Any further questions, gentlemen, ladies? No? Well, thank you so much for this fascinating presentation. I think we look forward to seeing your software come out and getting to use it. Actually, I wanted to ask if anybody has any images to share. Maybe something of the Neowise comet, perhaps, or anything else that you guys have been able to get out and see. Otherwise, I guess we will adjourn our meeting. Next month, we are going to have Eric Coles presenting. Eric is a fantastic imager. He's one of the people who helped run the Astro Imaging channel that you're probably familiar with on YouTube. And a real nice guy, and I look forward to seeing him here, and I hope I see all you guys here too. So come back next month. All right.
Thank you very much for the opportunity. I appreciate it. And I like the motorcycle.
Ah, Paolo, he likes your motorcycle. I do too. All right.
Thank you very much. Good evening.
Thank you. Thank you, Doctor.
Thank you. Bye.
Bye.
Bye-bye, everybody.